Hello, and welcome to the webinar, Forecasting Innovation from Today's Nobel-Quality Science. My name is Anthony Schiavo, Senior Director and Principal Analyst here at Lux Research, and I'll be moderating and presenting during today's session. Joining me for this discussion is my colleague Ari Van Berkel, Chief Product Officer here at Lux Research. Throughout this webinar, you can type any questions you have into the questions box on your screen. Time permitting, we will answer all the questions we can. If your question does not get answered, please do not hesitate to email it to questions@luxresearching.com and we will respond. If at any point you experience technical difficulties, such as a frozen screen, simply refresh your browser and check that your internet connection is strong. And with that, let's jump into the presentation. Ari?
All right, thank you, Anthony, for the introduction, and welcome everyone. Good morning, good afternoon, or good evening. It's my pleasure to join you again in one of our webinars. And today we are going to talk about how we track technology and, more importantly, how we find technology. We just updated our Lux Radar, which is our way of tracking and evaluating technologies. And in the Lux Radar, we look at technology in terms of their momentum, how much interest is there, how much people are working, in terms of their transformative capability, their potential, their innovation prowess. And we rank those this year, all of the technologies that we track, and it leads to a top 100, give or take. And that's the technologies we follow. And you can see the changes in the ranking every 6 months, because we update those every 6 months. So that's all good and well, but how do we know which technologies to look at? How do technologies make it to the list that we evaluate? How do we find those? Now, one of the ways to do that, of course, is to listen to our clients, and they frequently come up with new suggestions. And of course, we find things in conferences and in other conversations. We look at our analysis of what is really needed, what are the big problems and what could be potential solutions. But one of the more interesting ways we look at this is to look at scientific research, because scientific research and breakthrough research really creates completely new capabilities, allows us to do something that was not even possible before. So that's what we're going to look at today. And since this month, of course, is the month that all the Nobel Prizes are being awarded, we are going to look at the Nobel Prize as an innovation tool. And we're going to discuss that. And that will lead to an understanding of innovation. And we have a 3D model of innovation out of scientific research. And we'll present that model to you. And then finally, based on our model, that I think we can convince you that it actually works, a model can predict, and we can predict what are some of the next Nobel-Quality innovation breakthroughs that you should be watching. So we'll leave you with some things to watch that will definitely also make it on our watch list for the Lux Radar. But before getting into all of that, of course, we need to talk about Nobel Prizes and about this year's Nobel Prizes, and we really want to congratulate the Nobel Prize winners. And we'll be looking at chemistry and physics, so not at all the Nobel Prizes, but chemistry and physics, that's what we're interested in. So the Nobel Prize for Chemistry this year went, of course, to Susumi Kitagawa, Richard Robson, and Omar Yagi for their work on metal-organic frameworks. So congratulations to them. And then, of course, physics had a really exciting topic and somewhat bewildering topic of macroscopic quantum tunneling, right? Star Trek level stuff going on there, and quantization in electrical circuits. And that Nobel Prize went to John Clark, Michel Devoret, and John Martinez. So also congratulations to them. And of course, I fully expect all of these people to watch our webinars regularly. So I hope they get it firsthand, but otherwise, maybe some of you can pass on our congratulations. add some older Nobel Prize winning research as an example of how scientific research eventually gets converted into new possibilities and into new innovations. And what's particularly interesting to me, as some of you may know, I'm originally a mechanic lost into the realm of chemistry. Really interesting to me, this is molecular beam dynamics, because this is combining chemistry and Newton's laws. It is a molecular beam, so a very precise flow of molecules into a vacuum chamber and having them collide with other molecules. And when that happens, Newton's laws allow you to predict what will happen to those molecules. It is like colliding cars, right? You can predict, if you know exactly the angle and the properties of the cars that are impacting, you can predict where they are going to end up. And it gets even more exciting if part of the car ends up on the other car, of course. So, and this is what happens with molecules. So you have potassium being injected, and you have methane with one iodide atom instead of one of the hydrogens. And then an exchange takes place. So the iodide action you're interested in. How do you know that's really happening? Well, the collision and Newton's laws tell you exactly how these molecules would be scattering. And so now you can precisely see the reaction that's taking place. And this is, of course, a relatively simple, not quite simple, but a relatively simple reaction, but you can do that with more complicated reactions as well. This got the Nobel Prize back in 1986. So for research that was done already in the 1950s and 1960s at Berkeley. And John Polanyi, Juan Lee, and Dudley Herzberg won that Nobel Prize. So well done. There was some more to it. There was some infrared chemiluminescence also involved in the research, but it's not my purpose today to explain all of the research that happened there. What's interesting is what happened next. And the first thing that happened next is people got really excited about this, like I, basically. And they started doing all sorts of things. They were doing laser selective chemistry, basically using molecular beam dynamics and then exciting one of the bonds in the molecules with a laser to see if they could direct, if they could influence exactly what reaction would take place. They were looking at laser separation of isotopes. So can you excite one of the isotopes and can you then see it moving in a different direction from the others? They were looking at doing the molecular beam together with a solid surface. So can you also look at it and see what sticks to the surface, what are active sites, for example. And finally, some people were looking at unimolecular reactions, basically cracking. Can you make cracking very precise so the distribution of chain length after the cracking is predictable using coherent light, a laser, essentially. Now, it's very likely that you haven't heard of any of this. And the reason is all of this happened in about the decade after that initial research, but none of it made it into application. It was really interesting research, but then it didn't scale and it didn't become an innovative technology. What did become an innovative technology as a direct result of this scientific breakthrough are things like atomic layer deposition and chemical vapor deposition. And you can see the machinery, the equipment that was the result of that. So there's a scientific breakthrough, there's a lot of experimentation, there's a lot of excitement about trying to do interesting things with it. And some of it sticks and scales, and a lot of it doesn't. So what can we do with that? Now, there's another interesting example around some other Nobel Prize winning research. And I'd like to hand over to my colleague Anthony Schiavo here, who has done a lot of thinking about this particular research? So, Anthony.
Yeah, this is a very, what we've hit upon is a very interesting question, right? Which is there's this Nobel Prize, and it's for this very sort of interesting breakthrough research. But how does that translate into commercial funding and commercial success? And more to the point, how can you even recognize this really interesting research while it's happening? And this is a quote that this was said to me in conversation from a company that had funded Nobel Prize winning research. And you could tell that they didn't really know what they were funding. They were funding lots of different startups, lots of different academics, lots of different interesting areas. But it was a big company, and no one had particularly identified that this one particular research group was heading towards a Nobel. And you can see that this is a challenge even for the Nobel Institute. Sometimes they give the Nobel Prize very early in the sort of trajectory of a technology, right? With graphene, as an example, the Nobel Prize was given out in 2010 for something that was really only happening a few years ago, 2004. And this kicked off a lot of work on graphene and commercial efforts, and we'll get into those in the next section. But most of the key work was really after the Nobel Prize was given out. Whereas this year's winner, a lot of the key work on metal organic frameworks dates back to the 80s. There's been already a significant boom in commercialization. We have startups, we have companies trying to bring these materials to market. And it isn't until now in 2025 that we've gotten the Nobel Prize. So there's this, I think, very critical question and this very critical problem that these scientific breakthroughs are hard to track and they're hard to understand, right? It's hard to identify when is this happening and what is the impact going to be. And for science-driven companies like our clients, this is a real challenge. And I think this is really ultimately what we wanted to try and provide some guidance around during this presentation, Ari.
Right, so one way to look at it is to think of it in terms of generations. And this is key to our model. So the 3Ds that we are going to introduce is discover, dabble, and deploy. Originally, we were thinking of it as discover, tinker, and deploy, but tinker, of course, is not a D, so we opted for dabble. The point here is about generations. So there's, and the generation aspect is critical to this model. There's a first generation that discovers the scientific breakthrough. This first generation teaches to a next generation who now has a much earlier understanding, of course, in their career of the breakthrough of what it's all about. And they start to dabble. They start to think, what can we do with this? They start to try things. The second generation passes on all of those experiments, whether they succeeded or not, to a third generation, which is then ready to start deploying. Doesn't mean they do deploy. There can be a delay, and we'll get to that in a moment. But the fact that you need at least 3 generations of students to go from a breakthrough to a real innovation that you can deploy at scale is quite fundamental in our experience to scientific breakthroughs. So, and 3 generations of students is like 3 generations of PhD students is 10, 12, 15 years. That kind of time frame is what you're looking at. So if we look at some of the Nobel Prizes, right? For example, giant magnetoresistance. Nobel Prize of Physics, 2007, awarded to Albert Firth and Peter Grunberg. Discovery was 1988, which the discovery was showing that you can change electroconductivity by changing magnetization. So if you change the magnetic polarity, then you change the electric conductivity. Interesting. Dabble started quite immediately right after, right? Right, the next generation started to dabble, and they had a fair idea what they could use it for. Obviously, this was where disk storage and magnetized storage was already happening. So they were thinking about designing hard drives and things like that. And dabbling was mostly about the design rules, figuring out how to properly design this. And then in 1987, the first hard drive that used this phenomenon was launched commercially. So this is a fairly straightforward deployment of a scientific discovery, and it takes about 10 years. Here's another one, lithium-ion batteries. I think we're probably quite familiar with that, all of us, right? John Goodenough, Stanley Whittingham, and Akiri Yoshino won the Nobel Prize in 2019, were awarded the Nobel Prize in 2019 for chemistry. But it was based on a discovery that started in 1976. It's actually a couple of publications that are key publications. The earliest one was 1976. There's some others in early 1980s. But they looked at intercalation materials, so materials that could absorb and release the lithium as you charge and discharge the battery. Dabbling started about 9 years later, looking at electrolyte materials, looking at safety improvements, all of those kind of things. And then the first deployment happened about 6 years later when Sony released their first lithium-ion cell. So this is a discovery that took about 15 years from discovery to deployment. And since then, lots of things happened, and we all know the story about how lithium-ion batteries scaled tremendously after that. So these are two that fit our model quite well. There's a discovery phase, there's dabbling, there's deployment. Now, Anthony, how does that work with graphene? Does it fit our model equally well?
It's a little bit more challenging, right? So, graphene, we had in 2004 this discovery really of a production method, right? This is a very famous sort of pop science discovery that you could produce graphene layers by taking regular tape and Scotch tape and peeling layers of carbon off of each other until you got down to a single atom thick. And this allowed them to isolate and to test the properties of graphene for the very first time. And very quickly, things were moving into the sort of dabbling phase. There was a lot of hypothesized applications and even tested applications. The properties of graphene, especially at that nanoscale, were very impressive, whether it was in terms of strength or electrical conductivity, thermal conductivity. But ultimately, in a lot of ways, we're still in that dabbling phase today. We've certainly built a large-scale production capacities for graphene. So in that sense, we have reached the deployment phase. We've used it commercially in coatings and additive materials. But I think we're still far from a killer application, right? Or a clear use case that really is going to drive and create a meaningful market around graphene. So in that sense, we haven't really gotten to that deploy phase, not the way something that lithium-ion batteries have. And I think what's interesting is that you can see this signal very clearly on the Lux Tech signal. This is our proprietary benchmark. We showed this a little bit earlier of papers, patents, government funding, VC funding, tracks all this data, and it really looks for changes in the momentum, changes in that signal. And you can see that right around that Nobel Prize, we really started to see that uptick, right, in innovation activity that really kind of signals the onset of that dabbling phase to us. And, we can see that this pattern has played itself out in fullerenes as well, right? You have the discover phase in 1985 with the discovery of these sort of buckyballs, as they're called, Buckminster fullerenes, these sort of spherical cages of carbon atoms. Almost immediately, we move into the dabbling phase. There's a lot of excitement around the potential use cases, everything from drug delivery to solar cells, composites, some very high performance electronics applications. And today, again, we're not really in that, what I would consider a deployment phase. Yes, there are commercial manufacturers of buckyballs, quite small, one here based in Massachusetts, where I live, actually. And there are some commercial uses in things like photonics. There are some very specialized photoresists that use buckyballs. But again, not what I would consider to be a killer application or a major sort of commercial deployment. And when we look back at the history of metal organic frameworks, you can see that there is this sort of long history dating back from this theorization in the 50s, some of that initial synthesis, which won some of the initial work that won the Nobel Prize this year. By 2003, we had the first manufactured production of these in an academic environment. One of the things about metal organic frameworks is there's a huge variety. So it took a while to go from the first synthesis of a moth to the first synthesis of a moth that didn't immediately fall apart or get, react with its environment. That took about a decade, maybe more. And then by 2012, we had the beginnings of commercial activity, and even the first commercial products, which were launched in 2016, ultimately failed, not for technical reasons, but for patent infringement reasons, really more like copyright or sort of IP infringement reasons. And then, 2025 with the Nobel Prize today, and there's still a lot of commercial work happening on metal organic frameworks, right? And you can see, again, we have tracked the onset of this dabble phase quite clearly, especially kicking off in 2012. But there's a real uptick starting in the 2000s that we can begin to track quite clearly, and then quite strongly in that 2012 era. So I think what's clear from this analysis is that we can track and identify the dabble phase. And often we can move into the dabble phase pretty quickly. So what we need to do is use that information, right, to both plan our innovation activity, but also find a way to sort and monitor these technologies out from each other. And so, Ari, maybe you want to say a few words about the sort of the quantum tunneling application before we get into maybe how we can use this information, right?
Yeah, we'll see more about that. So, of course, we talked about net organic frameworks, and the other one that won the Nobel Prize, was awarded the Nobel Prize this year, was the macroscopic quantum tunneling. As you can see again here, dabbling is starting relatively quickly, but is a very prolonged and not very active tech signal. And it's only really taking off a bit more right now with more interesting quantum technology in general, I would say. So here, clearly there's a dabbling phase where people are highly intrigued, and it is a very intriguing scientific breakthrough. Really think there should be something that they could do with it, but they're quite unsure what that something would be, and haven't quite solved it yet. There's no killer application yet. So if we look at all of the Nobel Prizes of the past 40 years, so we look at everything that has been awarded since 1985, and we look at the chemistry and physics prizes, and we divide them into discover, dabble, and at the very top, the deploy phases. We get a picture more or less like this, where we've ranked them not according to when the prize was awarded, because we've argued before that that's not a very clear signal. We've ranked them according to when a key publication was made. You'll find that there's actually one publication that is still before the Second World War that is still in this data set, right? It's 1985 Nobel Prize for physics, actually, which is about electron microscopy. So the electron microscope got a Nobel Prize quite late, actually. And this is a 1931 publication, if my memory is correct. There's a couple of things that are interesting here. First, physics has a much harder time making it to the top of this chart. So physics takes longer and is more difficult to get to the deploy phase than chemistry. Chemistry has an easier time finding interesting applications or killer applications sooner, apparently. And you could see that about 1/3 of the Nobel Prizes in physics and chemistry, the total mix, that were awarded in the last 40 years are still actively dabbling. So you could say this is your watch list. This is where interesting new breakthrough innovations can still emerge. Don't have to emerge, but this is where you have to watch what interesting things people are doing. So just out of the total watch list, a quick selection. If you look at the 2016 Chemistry Nobel Prize, molecular machines, Mr. Veringa, among others. Why would you watch that? Well, there's lots of interesting dabbling going on there with molecular elevator switches, even molecular vehicles, molecular muscles. There's bound to be some interesting applications there. Right. The 2011 chemistry Nobel Prize was awarded for quasi-crystals. And this is getting renewed attention now because those quasi-crystals could present an interesting way to develop PFAS alternatives. But also low friction coatings, novel catalysts, and hydrogen storage. Although I think hydrogen storage, we're kind of past that right now. So maybe not watch that too much. 2001 physics, Bose-Einstein condensation. Lots of things right happening in photonics. We're capturing light, we're freezing light using Bose-Einstein condensation, so we could create photonic computers perhaps. Lots of dabbling still happening there. High temperature superconductivity, the 1987 physics prize. Power transmission and quantum computing depend on high temperature superconductivity, or at least could benefit greatly from it. And finally, the 2012 physics prize, control of individual quantum systems, which is used right now already, starting to get used in quantum sensors. And of course, after that, you can look at things like quantum computers as well. So this is an interesting watch list, but it's certainly not the only watch list. It's what we thought we would highlight to you in this webinar. And moreover, there's more than just Nobel Prizes, obviously. So how about predicting innovation breakthroughs with or without a Nobel Prize? And Anthony, you did quite a bit of work on that and looking at all of the things that we are covering and see if you could detect the dabbling phase, right?
Yeah, absolutely. I think what's interesting about this, right, is we've sort of developed this fingerprint for the dabbling phase. We're looking at innovations with relatively low total activity on the tech signal. But we're seeing that sort of high momentum, right, that high growth, especially in the last 2 years. And the challenge with the Nobel Prize, as we've kind of discussed, is that this dabbling phase can last a long time. And the way I think to flip that on its head is, instead of waiting for the Nobel Prize Institute to award their prize, as wonderful as they are, if we go out and we look proactively and we hunt down technologies that fit this fingerprint, but are also aligned with some of the key needs and key drivers that we understand in industry, we can identify really impactful science at an early stage without having to wait for the Nobel Prize. So that's what we did. We scanned more than 3,000 Lux tech signals. We did a bunch of data crunching. We sorted them by these different factors, looking for those ones with high momentum. And these are a couple that I pulled that fit the bill that I think are also aligned to some of the key megatrends we're seeing in the space. So the first is YCBO superconductors. These are for your supposed high temperature superconductors, right? And these have been in discovery for a long time. It's been pretty well known. You can make these superconductors. The challenge is really manufacturing them, right? And getting them into a usable form. These are ceramics. They tend to be very difficult to draw into something like a wire, which is a really helpful thing to have if you are wanting to produce any type of useful product. But in the last few years, we've seen the rise of data centers and AI as key topics, along with interest in fusion as an energy source. And this has prompted a lot of renewed interest in superconductors. And we've really begun to see this research begin to move from that sort of discovery phase into much more, kind of like you were saying earlier, Ari, getting into the methods and the approaches to actually make the design parameters to really make a useful product, whether that's putting these on tapes or getting them into other form factors that really start to make sense. And you can really see that activity in the tech signal, which has been declining basically since the discovery and the initial level of interest. Now we see this big uptick in the last few years. And that's, to me, a real signal that we're in this dabble phase. Secondly, I would call out titanium nitride superlattices. This is a really complex material. I won't get into all of it, but you'll have to just take it on good faith that these are really interesting from the perspective of making optical and optoelectronic metamaterials. You can produce materials that have really unique and quite different optical properties, and can allow the creation of meta lenses for things like imaging, sensors, potentially photonics applications. And again, here we're seeing the same sort of thumbprint. We had some initial work and now a clear uptick starting in 2020. That's driving us much more into manufacturing, into design, into systematizing from this sort of invention discovery phase that we were in to now a more dabbling phase where we're getting to get the initial elements of what a product might look like. The third thing I want to highlight would be recyclable curing agents. There was some initial work on this in the late 90s, but things really sort of kicked back off in a research phase in the 2010s. But these curing agents, again, have seen a real bump up in activity starting around the 2019, 2020, 2022 timeframe. And again, I think there's, we see this signal, this thumbprint, the innovation data, but there's also a clear draw from industry, right? It's becoming increasingly clear that things like wind turbine waste are going to be major recycling challenges in the future, and that some of these new solutions are going to be necessary, right? And so we're beginning to have corporations get involved and begin to really think about, okay, how do we productize some of this research? How do we turn this from something that's more like a, a science project into something that's a bit more usable? Begin to develop the right formulations and actually test these applications. And then this last one is so interesting to me, maybe my favorite. It's aluminum nickel cobalt magnets, Alnico magnets. And what's different about these is that this is something that's been deployed for a long time. Alnico magnets are not new, right? This is a technology, a product that you could buy in the 70s. For a long time, these were some of the strongest magnets around, at least until they were displaced by rare earths. But something funny started to happen. Despite the fact that this technology is really in a lot of ways mature, research has begun to pick up, especially in the 2000s. We saw some growing interest, and then that sharp spike up in a couple of years, starting in 22, 23, that's to us, that's really characteristic of moving into this dabble phase. What's driving this, we think, is that Alnico magnets, although they're weaker than rare earth magnets, they don't contain any rare earths, right? And their current performance is actually much less than the theoretical limit of what their performance should be. If their crystal grains were bigger, they could have perhaps 2 or 3 times the magnetic strength. So there's a lot of really interesting and fundamental research that's been happening. Okay, how do we control the grain properties? How do we control the crystal properties of these structures? And now we're beginning to see major magnet manufacturers get involved. We're seeing this new research begin to translate again into those commercial recipes, those commercial products, essentially productizing that research. And of course, this is aligned with a huge number of challenges, whether that's electric motors and EVs, the need for a better, higher performing magnets and things like storage, data storage. There's really a wide range of different potential applications. And the fact that these are not rare earth containing has taken on a really important political valence. So it's not just these sort of new or very fundamental breakthrough technologies. You can actually see this pattern happening in these mature technologies that people are coming back to. So I think what this shows is that we can actually go out and, with a targeted view, find the technologies based on the signal from that we developed from the Nobel Prize, find the technologies that are going to be really most impactful for us in the energy transition and the innovation space going forward. And we can do this, pretty reliably at scale.
Right, so we know there's a generational effect where you have a discovery phase which needs to be transferred to the next generation, which has the time and the energy to start dabbling, and then it goes to deploy. We know we can track the dabble phase, and we also know roughly what we need to watch in the dabble phase to see if it's heading towards deploy, which is people getting settled on one or two applications and starting to really work on design rules for those applications. So you have to track that start of the conversion of science from science to invention. So not just track the scientific efforts, but really track how that conversion works. And that conversion works by trying a lot of things, settling on one or two things, and starting to create the design rules for those killer applications. And once you see that happening, you know that you're looking at the onset of the conversion from science to invention. Now, this is a great time to do this because we now have great tools at our disposal, right? So we can track developments using data science. And at Lux, we're tracking thousands of developments already. So whenever you come across an interesting breakthrough, just put it in your system, or at least we do it. We put it in our system and we can track it and we can detect the onset of the dabbling stage. And then we can look at the dabbling stage and we can see if that's an interesting dabbling stage or if they're still just trying to find their way around it, right? Just trying things. So it's very difficult to predict where a scientific breakthrough is going to make a difference, right? And that's the third key takeaway that we would like you to take away here. Dabbling can take you in all kinds of directions, and some of them are unexpected. So some of them you will not have thought of in relation to that scientific breakthrough. So look at the onset of the dabbling phase, then look at what people are dabbling with. Look at the patents and the publications that are going on. Keep an open mind, and then pick winners based on what you see in all the dabbling. And again, a good indication of winners is when people are starting to create design rules, when they're getting into the particulars of how to use this and how to really scale this. So with that gets us to the end of our webinar for today. And I think, Anthony, we ran a bit long. We had a lot of interesting stuff to share, but
we did.
Let's take a look if there are any questions from the audience here.
Yes, Ari, there are questions. Like you said, we ran long. We don't have time for many. I think the big question, which I would sort of synthesize from a couple of these, is what's next? What to do next, right? You've identified research that's of interest. How can you tell when it's going to move out of that dabbling phase and into a more commercial phase, or how should you engage with that research at that academic level?
Yeah, and when to engage, right? So that gets you back to that quote, right? We were funding hundreds of researchers, but we didn't really know what we were funding until they got a Nobel Prize. So assuming you're also funding a couple of researchers that don't get a Nobel Prize, but are still doing quite interesting stuff, right? How do you detect that, and how do you detect what's interesting dabbling and what is fascinating but not commercially interesting? And I think there's no easy answer there. Like I said, it really is about, and then we're getting back to some of our other models that we use at Lux. You have to look at what are the limiting factors to deploy this technology. If you look at metal organic frameworks, the limiting factor is manufacturability. We know what some of the killer apps could be for metal organic frameworks. We just don't know how to create it commercially because we don't know how to manufacture them at scale and at an affordable price. So once you've done that analysis, if you've seen interesting things happening around the scientific breakthrough and you see people dabbling, take a look at what the rate limiting factor is for deployment. And if people are not working on that rate limiting factor, then expect dabbling to continue for quite a while. And of course, you can intervene and you can say, hey, I want to invest in that rate limiting factor. I want to change the research landscape, which is quite feasible if you're a company and if you have the right network. So that's the other element that I would like to convey based on this question. Your ecosystem, the network you have is a long-term investment. It's an asset. So you also invest in collaborations with universities, not just based on their current research, but also based on a general area of research that you're interested in.
All right, and with that, I think we're going to conclude this webinar today, given that we are a little short on time. I just want to thank you all for joining us. The slide presentation and recording from this webinar will be sent out to all attendees via email today. After leaving the webinar, you will be prompted to complete a survey on today's presentation. So we'd really appreciate any feedback you have that may help improve and inform future webinars. And I'd encourage you to check out our future and upcoming webinars. Look at them on our website, and you can look at all the other fun things we do here. Thanks so much for joining, and have a great day.
Thank you.